Welcome back to my Databricks series. In this video, we will go through the evolution of big data from databases to Apache Spark. In the first video, we explored what Databricks is and why learning it can really boost your career as a data analyst. But today, I want to take you a step back in time to understand how Databricks can exist in the first place. Because to truly appreciate its power, you need to know the story how data technology evolved from old school databases to Hadoop to Apache Spark and finally to Databricks Lakehouse. But before we start off about Apache Spark and Databricks Lakehouse, it is important to have a clear understanding of big data. Big data means extremely large amount of data that are too complex to be handled or analyzed by a traditional tools like Excel or regular databases. Some of the example of big data are think about of all the messages sent on the WhatsApp every second, all the credit card transaction happening around the world, or all the GPS signals from your phones and cars, or also think of all the social media content on the Instagram or YouTube or any other social media platform. That is all big data. So every time you scroll Instagram, send a message, or make a online payment, you are actually contributing to big data. Behind the scenes, companies are working hard to make the sense of this massive flood of data. And that's exactly where technologies like Apache Spark and Databricks come into play. Now, you must be thinking that it is called big data because it handles huge amount of data, but this is just one of its characteristics. Basically, big data has a five key components that is also called five V's of big data. First, volume. Big data consists of huge amounts of data. Take example of billions of WhatsApp messages we exchange every day. Number two, velocity. The speed with which data comes to you. You can take example of how stock prices changes every second. Variety. It can store many type of data ranging from structured to unstructured data type. Example, text, images, audio, video, log files, sensor data, and many other data formats. Veracity refers to the reliability, accuracy, and trustworthiness of data. Value. Value represents potential insights, knowledge, and business value that can be derived from big data. That is what analysts do. They derive insights, patterns, trends from these big data and help businesses to take rightful decisions. On premises data warehouse. Before the big data revolution, companies relied on traditional warehouse running on their own servers. Scaling meant adding more CPU's power or RAM to a single machine, what we call vertical scaling. Before framework like Hadoop, organization typically stored their data in a data warehouse on a on-premises servers. When the data volume increased, they typically scaled the resources vertically. This means increasing the capacity or the power of computing resources. This can be done by adding more CPUs or RAMs, for example. Think of it like trying to upgrade your home computer by stuffing more and more RAM stick until you finally run out of slots. At some point, you can't upgrade further. You need a way to grow. There were many other limitations of scaling vertically. Vertically scaling typically requires downtime or system disruption during the upgrade processes. Since the modification is applied to a single machine, additionally, vertically scaling becomes increasingly expensive as you move high-end hardware and making less cost effective for rapid data growing. And since all the data stored in a centralized system, it also creates a single point of failure. If centralized machine crashes, the entire system can go down. That is where Hadoop came into rescue. To overcome all these challenges led to the rise of horizontal scaling through distributed computing framework like Hadoop, which could store and process massive data across many low-cost machines. In 2002, Google published a paper storing large data sets using a distributed file system called GFS or Google File System. In 2003, they published another paper on a framework called MapReduce for distributed processing of large datasets. The Hadoop framework was created to address the challenges of storing and processing large scale datasets in a distributed computing environment. It was designed to provide a scalable, fault tolerant, and cost effective solution for handling big data. Hadoop aimed to provide distributed file system called HDFS, which is abbreviation for Hadoop Distributed File System. Hadoop introduced a processing model known as MapReduce, which facilitated the parallel processing of large datasets. MapReduce allows users to write distributed computation that can be executed in a parallel across a cluster of machines. To put it simply, imagine you have a massive dataset. Instead of keeping it all in one powerful machine, you break it into a smaller pieces and store them across several computers in a cluster. Now, as your data grows, you don't need to buy a bigger and bigger machine. You just add more computer to the cluster. It is like adding more workers to an assembly line instead of depending on one superhuman employee. In terms of benefit of this, it has distributed architecture. That means Hadoop is capable of distributed storage and distributed processing along with scalability. Another advantage is fault tolerance. By breaking down the large dataset into smaller chunks, the chunks can be replicated across the different nodes. So, if there is a hardware failure in a individual node, the data is still available in another node. Cost effective. It uses commodity hardware instead of expensive specialized servers. Hadoop can also work with various tools and technology as well as wide range of data types from structured, semi-structured, and unstructured data. Hadoop was revolutionary. For the first time, it allowed ordinary computer to work together like a team instead of relying on one expensive supercomputer. But even the best team can slow down if they have to write every idea on a paper before acting. That is exactly what Hadoop's MapReduce did. It wrote everything to disk again and again. One of the biggest limitations of Hadoop's MapReduce was its heavy use of disk storage because it constantly read, write data to disk. It ends up performing a lot of disk IO operation, making it much slower compared to modern in-memory framework like Apache Spark. Another challenge was its complexity. Coding in Hadoop wasn't easy. It requires long, detailed programs and wasn't very user-friendly. Apache Spark. These challenges with Hadoop opened the door for something new, a faster and a smarter way of processing big data. That is how Apache Spark was born in 2014. It was designed to overcome the Hadoop's limitation and offered a more flexible, developer friendly platform for big data analytics. Instead of constantly reading and writing data into disk, Spark keeps data in memory, which makes it lightning fast. In fact, it can process data up to 100 times faster than Hadoop's MapReduce. Imagine a report that took 10 hours with Spark. You could get the same result in few minutes while you still sipping your coffee. One of the biggest advantage of Apache Spark is its ease of use. Unlike Hadoop's MapReduce, Spark is designed to much more user-friendly and developer-focused. It provides simple, high-level APIs that work across multiple programming languages, including Python, SQL, Java, Scala, and R, making it accessible to both data engineer and analyst. Another great feature of a Spark is its modular design. You can use the same engine for different kind of workloads, from batch processing to real-time streaming, machine learning, or even graph analytics. Spark come with a built-in libraries for all these tasks, such as Spark SQL, Spark Structured Streaming, Spark ML Live for machine learning, and GraphX for graph analysis. And finally, Spark is known for extensibility. It focuses purely on fast, parallel computation, not on data storage. This means Spark can connect to many data sources, including Hadoop distributed file system, cloud storage, and traditional databases. No matter where your data lives, Spark can process it in memory, give you powerful speed and flexibility within a single platform. Now, let's talk about Apache Spark ecosystem. Spark isn't a single tool. It's more like an entire toolbox for a data professional. Within this ecosystem, you will find different component designed for different kinds of data work. You have got Spark SQL for queries, Spark Streaming for real-time data, Spark ML Live for machine learning, and GraphX for network analysis. At the foundation of all it lies Spark Core, the base engine that provides essential functionality and API. However, Spark Core by itself can be quite complex to use, especially for advanced operations. It was mainly used in the early days of a Spark and is no longer recommended because its lack performance optimization and ease of use. On the top of that foundation sits a higher level layer, a more user-friendly abstraction over Spark Core, which has become a very popular among data engineers, data scientists, and data analysts. Spark SQL allows you to query structured and semi-structured data using familiar SQL syntax. It also provides a powerful data frames API and support integration with various data sources, making it data manipulation and analysis seamless. Spark Streaming enables real-time data processing and analysis. It takes incoming data into a small micro batches, applies transformations, and generate insights in a near real time. Spark ML Live is a Spark's machine learning library, offering a wide range of algorithms and tools for building and deploying scalable machine learning models. And finally, GraphX is designed for graphs processing and analysis. It lets you perform computation on graph structured data, such as running graph algorithm or analyzing social network connection. Together, all these components make Spark a unified, powerful, and versatile platform for modern data processing. The Databricks Certified Data Analyst Associate course mainly focus on a Spark SQL, which is ideal for professionals working as a data analyst, business intelligence specialist, or similar roles. So that brings us to the end of our journey from traditional data warehouse to Hadoop and then to Apache Spark, the powerful foundation that made Databricks possible. Each step in this evolution solved new challenges, helping data processing becoming faster, smarter, and more collaborative. In my next video, we will take this story forward and explore Databricks Lakehouse platform, how it brings together the best of the data lakes and data warehouse, and why it is becoming the backbone of modern analytics. Thanks for watching. I hope this video helped you to understand not just what Apache Spark is, but why it exists.